thanks everyone for joining today. So before we get started, I just want to go over a couple items. If you are not familiar with XP Solutions and really who we are, XP Solutions, as you can see here on the screen, is a software development company for the engineering and technical services industries. So we have a number of products, including XPDRAINAGE, which Nicole already mentioned, which you may already be familiar with, XP Swim, XP Storm, XP Rafts, to name a few. So we have a handful of offices, 3 primary offices, one in Portland, Oregon in the U.S., one in the U.K., in Newbury, if you're familiar with the area, and one in Brisbane, Australia. So beyond those 3 main offices, those would be our main kind of support hubs. We have a number of distributors and have other contacts kind of around the world. So the sun never sets on XP Solutions, if you will. So it may go without saying, but we'll be looking at XPDRAINAGE here later on. And we are continuously improving and updating this software, XPDRAINAGE, as well as the rest of our suite of different software packages. So today, we're going to discuss a couple items. So we're going to start with green infrastructure conventional design practices. Okay, just a quick look at the general conventional design procedures that we're going to see in the field. Okay, and once we look at these procedures, we're going to find there are some gaps in these practices which will lead to some issues. So we're going to cover those gaps, what those issues are, and ultimately how these issues, how these gaps can be overcome by clearly visualizing our green infrastructure design. There'll be an example of this using XPDRAINAGE at the end of the presentation. Now, if some of you aren't familiar with some of these terms, that's okay. So we're talking about today the greater practice of sustainable stormwater management. Okay, so even in the U.S., there are different terms for this. So we might see low impact development, LID, be used. Maybe increasingly more commonly, you're going to see green infrastructure, GI, be used to represent that kind of greater idea of sustainable stormwater management. Now, with that being kind of the greater idea, the individual facilities which would make up this strategic plan, let's say, for sustainable drainage. And we can see on the images to the right, the lower image would be an individual facility. This would be a curb cut bioretention or a rain garden. We're going to refer to this as a stormwater control. Okay? The image above being maybe a small wetland area. These are the individual facilities. So the stormwater controls are the individual elements kind of making up this treatment train approach, this kind of greater holistic green infrastructure plan. So before we move forward, it'd be fun to get a little feedback from the group. I have a couple polling questions, so I'm going to ask these, and you can click on, I guess, one of the answers, and we can look at kind of what is the makeup of the attendees at the moment. All right, so the first poll is just simply, do you currently design LID controls? Okay, so I'll share these results. So you'll see that the vast majority of you have done this previously or currently do design these systems. Obviously, there's some that maybe haven't had a chance to do that yet, but want to learn more. Okay, so that's great. So it seems like the majority of people do this actively. So let's kind of see, what do people design with? All right. So if you do design, when you do design, what do you use? So I'll share this. And the vast majority of people are using spreadsheets, maybe even macro tools within Excel. Certainly beyond that, it's proprietary design tools or very advanced hydraulic models. That's kind of what I've seen to be the trend, which, beyond just the group here watching this webinar, that seems to be the general trend kind of across the U.S. Okay. So let's move into the conventional design, and I'm going to essentially touch on the statistics that we just looked at. So green infrastructure design. Now we're talking about water quality, right? Well, what we're going to find is we're not. In most cases, we're actually just talking about water quantity. Okay, this is a volume-focused design. There's a reason for this. In order to easily make a hand calculation, okay, and find this, we started with the assumption that, okay, we can imagine, using this picture on the right for a bit of a guide, imagine we go through a couple months of summer weather in a parking lot and there's no rain, so all of the brake dust accumulates, perhaps fertilizer, bark chips from landscaping, all of this stuff, okay, these pollutants, kind of accumulate in that parking lot, and then it rains for the first time in the fall. So we find that maybe the first bit of rain, let's say the first inch of runoff from our site, when it hasn't rained, that first flush, or we might call it the water quality event, water quality volume, that is going to contain, we're assuming, the vast majority of pollutants. Okay, so if we can treat that initial volume, well, then we're assuming we're treating the vast majority of pollutants, right? That's the assumption there. And with that assumption, we simplify a lot of stuff. We can just say that we can have a very simple equation to represent what that volume is, okay, what that first flush 1 inch is. So we can start looking at this problem immediately, ignoring the actual pollutant concentrations. So I'm not going to say that it's not important to actually model concentrations. It really is. But the conventional practices in the vast majority of the U.S. Are still tied to this volume containment, this volume treatment. Okay? So we have this first flush volume we need to take care of. That's this polluted bit of flow. And we're going to assume that if we can retain that water quality event, or if we can detain, let's say, 80% of that volume, well, then we're also treating 80% of the pollutants. Okay? That may not be the case, but that's the assumption we're making. So we're going to start by designing facilities, rain gardens, ponds, what have you, to retain this water quality volume, and then either bypass all greater storm events, or maybe we have more of a complex site, or maybe we're treating the water quality volume, but then on higher events in the same facility, we're going to attenuate the larger rainfall event flows to make sure that we discharge at or less than existing conditions. Okay? So design tools, well, we can use the rational equation for hydrology. That is the most basic equation you could use. Same with the Manning's equation. So we can get our hydrology volumes, perhaps with the rational equation, size our channels or pipes or swales, assuming the velocity and a number of other things, with the Manning's equation. Okay, that is, in brief, the typically used conventional green infrastructure design process. So with these calculations, the things we need to calculate, we're most often using spreadsheets. So I'll say either by hand or on spreadsheets. So where are some of the gaps when we're trying to design with a spreadsheet? So the first is our spreadsheet tool, our hand calculation, is literally disconnected from our site planning. So we're going to have our, let's say, Excel spreadsheet next to our physical plans sitting on our desk, our GIS or CAD files on the computer. They're disconnected, and that gap between those two systems is going to cause some problems. The next is during this design process, okay, we're going to have to rely on a simplified catchment delineation. Okay, so using a spreadsheet, using a hand calculation, we can really only look at one contributing drainage area at a time. Okay, we just can't very easily accommodate a complex system. So the third piece might be a bit following suit with, we have simplified catchments. Well, we're going to have kind of simplified facilities. So we can only design individual, independent facilities. And that is likely not what's being implemented in the real world. Okay? Part of the green infrastructure, sustainable stormwater management process is using distributed drainage across your site. Okay? Well, we're going to have a complex system that really isn't independent. Okay, so the first item where we're disconnecting our spreadsheet, so we see an example of some hand calculations and spreadsheets on the left. And of course, our CAD file or GS file on the right. Perhaps literally on your screen, you have two monitors and you have them on each monitor. Now, the issue with this is, what if I update one? The other is not automatically updated. The information is in one is not automatically referenced in the other. Okay, so we begin to start adding up all sorts of issues where they aren't representative of each other. Okay, so questions can come about. We can start having discrepancies from that. And this single item is where you're going to run through the most time and the most money on your project, especially if you have to revisit your design. Okay? So if you go and find, oh, there is a mistake, we changed our site plan, go back and change your facilities that you've designed in your spreadsheets. You have to start all over from scratch. Okay? And this is a big time sink on your project. So what are some of these gaps? So the first one is just simply the facilities won't fit on your site. So you are designing in a spreadsheet, designing by hand, and you might start with an initial area, but then your design says, okay, I need a basin that's so big. Well, that might not fit on your plan, and perhaps that's not updated, or perhaps the square footage area that you tell a site planner or site designer, I need this many square feet, and they cram that in somewhere, that maybe isn't the same thing that you were expecting. Okay, so it doesn't fit perhaps because it's too wide, too large. A big one, and very, very easy to overlook with these disconnected systems, is what about vertically? So let's say in a rain garden, we have a ponding area above, and then some sediment layer, some sand filter media. Maybe let's say that's 3 feet deep. So if your pond area is 2 feet deep, your filter media is 3 feet deep, you might have a 5-foot deep system. So can that gravity drain to the stormwater connecting pipe? Can that drain from one facility to another? So it's very, very difficult to understand if your swale will truly run and spill into your, let's say, rain garden, and then if that can connect into your downstream discharge point. Okay? Very, very easy to overlook. So the next item is not only, can we not easily sometimes tell what those levels are, but setting the elevations, and if there's grade changes perhaps in your site plan, is very tedious to make these updates, okay, to make sure that your design reflects your site plan. Since they're disconnected, very, very, very often there's going to be a difference, okay, and that could be disastrous. So a common one which is overlooked is, well, who created these design tools? So in some cases, perhaps for municipalities that have recommended design tools, maybe there's one person, perhaps a PhD candidate, that made this tool, this macro spreadsheet, and you lock it down and everyone can use that. But what if you need to make a change? What if you have a site and you need to have a little creativity and make something that's not the exact formula, the exact plan used in the spreadsheet? Well, you can't, right? And what if that PhD candidate, or what if this spreadsheet was written by the person who started a company? Okay, they had, let's say in '97, they created some calculation set and they put it into Excel at one point. Well, what if you don't have that person around anymore? Okay, and it's all locked down. You don't understand if it's correct, how to change it, Okay? Might sound a bit basic, but this is a huge hurdle, okay, with a lot of these legacy design tools. With these split design and site planning tools, we're going to very quickly be forced to design reactively. So we're going to design reactively based on the site designer's water resources judgment. So we're going to have a site designer give us a parking lot, give us some paved area, and then they're going to pick where the stormwater facilities can go. They might not be as familiar with green infrastructure design. They might not be as familiar with water resources design. But they're going to begin to tell us where facilities should go, how they're going to work. Okay? So right away, we are pushing stormwater to the back of the design process. When you can see from all sorts of discussions of green infrastructure how important it is to get the stormwater discussion to the very front of our planning and site design process. Going through these items, you're going to find that obviously constructability, the end of the project, is going to be jeopardized. So be it the construction schedule, maybe just the practical limits of implementation are all going to be affected. So an example, using a spreadsheet, even some maybe a little more advanced hydrology design tool, it might be difficult for someone, let's just say as an example, someone that hasn't had a lot of real-world site experience to understand that this dot in your software or this spreadsheet represents a manhole or a 5-foot deep facility in the real world. Okay, so that, if there's someone that doesn't have a ton of expertise, it's very easy for that to get lost. And then you'll find out that it's wrong when someone goes to build it in the real world. Okay, all of these items, it's going to force you to have many more design iterations than are required. Okay. So what are some of the solutions? Well, first and foremost, we need to design kind of within our background information. Okay, so we need to be able to draw things to scale. We need to be able to set things based on surface elevation. Okay, that's the only way we can make sure that things are up to date with our, let's say, our CAD files, our site plans. Okay, we have to be drawing these items kind of on these plans themselves. Like I said, drawn to scale. The important thing here would be the vertical nature of these facilities. We want to be able to see that, yes, the top of this facility is at the correct elevation and whatnot. Automatically sampling these elevations, but also lengths and surface areas based on how they're drawn, again, makes the design process transparent. We can see what's going on. Yes, this plan area isn't quite big enough, but that's all the area I have. Immediately you have to go back to your site design team, okay, and move something around, right? So it doesn't get lost in the process. Even a couple days worth of time, right? You do that on every project, or a couple times in a row, you're burning a lot of time that's just wasted. So one important visualization tool that's going to cut out a lot of mistakes is just simply a profile of the treatment trains. So let's say you have a swale and then a bioretention system. We need to represent these facilities in profile to see if they drain correctly to each other, to really get an idea of how they're storing the water, right? So maybe there's runoff draining to a swale. Maybe there is a spreadsheet you're using, and you're going to look at, all right, the swale is 2 feet deep, 1 to 4 batters, it's 100 feet long. Based on that, you know the volume, in theory, of that facility. Okay, well, what if in the real world that swale is at a 2% slope? Well, you're not going to be able to store water in that whole facility because it's at a slope. So really only one side will pool up to the top. The other side isn't quite full, right? So the volume estimates, and we'll see an example of this later if that doesn't make sense just being spoken. But we need to understand how storage is occurring, how infiltration is occurring, and how all the facilities can drain to each other. So that last point, how they drain to each other, the inter-watershed impacts, we have to understand, we have to be able to see in order to really know that our facility is going to work. Okay? Even if we went very conservative and individually designed facilities, and it was okay, and it was still appropriate to do, likely you're going to be very much so over conservative on the size of these facilities. All these items are going to lead towards just simply more confidence that the system as a whole is going to work, okay, and work for all rainfall events. That's what I'm getting at there. Okay, so we want the water quality event to be treated, but also there's more than just that one-inch runoff storm. Okay, we have a number of ARI events. All this, we're going to reduce the design iterations. Using green infrastructure well, or using green infrastructure practices better than we're currently doing, is going to save us site area. So we're going to be able to squeeze in one more lot. And obviously, all of these, that's saving money. Okay, the next gap, design procedures are, these spreadsheets are just dependent on simplified catchments. So you can see here there's an existing and developed catchment plan. Okay. So you can see here, even in the existing scenario, this isn't really one catchment. Okay. We're developing a parcel of land, let's say, which was purchased. I doubt that parcel was split up based on its catchments, right? So drainage isn't how parcels are laid out in a lot of cases. So drainage might not exit the site at one point, even in the existing scenario. Certainly, even if that was the case in our design scenario, where we're beginning to pour curbs, wow, that flow is going to be redirected, and likely we're going to have facilities cascade to one another, catchments combine in different facilities. Okay. Since we're limited with these spreadsheet tools, we're forced to simplify the catchments. We're going to get a poor understanding of what the true overland flow paths are going to be. And really, I guess even more importantly, this is rarely the case. So what if you have a complex site with more than one catchment? It begins to be extremely difficult, if not impractical, to try to design that with spreadsheets. Okay. How can we overcome this? Well, what if we could just simply apply some rainfall to our site based on a surface and find, right, where that runoff is going to go? Okay. We're going to be able to see, we're going to call this the deluge. We're going to deluge our site. We're going to find where that overland flow will pool up, the routes it takes to get there. So right away, without doing any site planning, we can know perhaps where we could focus our treatment train. Maybe the center of the site is where all the flow moves to, so we can have a system of swales or a system of bioretention. And we're going to cut down on cut and fill and a lot of problems later on in the design process. Okay, having beyond just visualizing where the runoff will move to, being able to have a complex system where we can allow multiple catchments to drain to multiple facilities, that is the treatment train approach that I've been referring to. And that is not only more realistic, but also you're going to be able to get a better design if you can visualize that. Okay, the third item here. So we, following suit a bit with simplified catchments, we have simplified stormwater controls. So we can see here we have these, Excel design tools for individual facilities. But, okay, we have a design tool, let's say for a water quality volume event. So we're going to design a single facility for just the water quality volume. Okay, so this facility is so big that it can retain this amount of volume. But then what we bypass the rest of the flow, and how do we calculate this bypassed conveyance? This might be when, do we have a separate pipe sizing spreadsheet? Do we have perhaps, this is when we turn to a little more advanced software just to model the pipes? So we begin to kind of get out into multiple different applications and calculators. That obviously the more different calculators and tools you use, the more risk you're going to have of error and just simply this discrepancy between them. So obviously with a spreadsheet, we could look at a facility, with just a storm event, with the water quality event. But what if you have these multiple use facilities, like a dry swale, okay, or an infiltration trench? So maybe during a low flow event, the water quality volume is treated by that facility. Okay, so we can infiltrate the water quality volume with this dry swale. But for higher events, that swale is going to kind of act as a attenuation facility. Okay, and we can store volume in the swale so that we can release it at an appropriate rate and release an appropriate volume. That is something we really can't do with spreadsheets. Okay. Really, all of this sums up if we can just have one place with all this information. So one package to design all this in with all of our calculators, with all of the required pieces. That's the only way to ensure we have the coherent design. Okay, so if we can have all of our designed facilities, all the catchments, all in one piece of software, it's the only way we can do it. So here, I guess, to visualize what we've just been talking about is XPDRAINAGE. So here would be a moderately complex site, okay, drainage inflow areas drain to different facilities. So on this one plan view, we're going to be able to look at the flow exchange between these different treatment facilities. So we have a bioretention, okay, which drains perhaps to a dry swale. You can see there's that trench underneath the swale. We can have porous paving. All of these drain down to a pond, and on this site there's 8 different catchments all draining together. Okay, this one place is kind of how we have to do this. To visualize these all together is going to overcome all the items that I brought up. So XPDRAINAGE, if you haven't seen it before, we're going to be able to kind of assist the user. The ribbon on the top is our workflow. So we're going to use the ribbon to start with the site background information, and then pollutants and design tools, ultimately down through our analysis and results. Okay, so we have just this workflow built in, right, to help you move through your design process. Deluge, the site, that's what I mentioned before. We have the ability to very quickly run a 2D simulation on our site and find those flow paths, find kind of the hot spots of where the runoff will pond up and move across our site. One important thing to note is that we have, I guess, not only the ability to look at quantity, which I've been talking about is kind of the conventional way to do it, though we can look at quality as well, that true pollutant concentrations, perhaps pollutants are being generated from catchment areas and then treated through different facilities. So we can have a very complex site looking at different catchments contributing different types of pollutant levels, and with different facilities, multiple facilities, at the end of our site we can quantify the actual pollutant load reduction. Okay, that's really the end game. That's what we want to do. So something else to help, we might have a lot of different rainfall sets, a lot of different stormwater controls that we want to use. Okay, well, that's something we would say this as a template. So we have templates that we can save our designs to. So when we have our bioretention that we use on all of our projects, this can be essentially copied from one project to another, or even just use the same facility, different areas on your site. Okay, so it's very easy to use the same facilities and kind of automate your design process. Pre and post analysis, a lot of what we'll be doing is we want to make sure our development does not discharge from our site worse than the existing conditions. So we don't want to impact the surrounding ecosystem worse than before we got there. So clearly there's graphical results. Also there's tabular results we're going to look at. Here's just a screenshot of the graphing system. So all of the comparison that you'd want is right there. I think this part is maybe the most basic concept, but the most important in practice is a profile of the results. Okay, so we have our treatment train. We can look at how the levels in these facilities interact. You'll see here in this screenshot this bioretention on the left. There's this little triangle with a half-flooded house. Okay, this facility is about to overflow, so I'm getting a warning here. This is my freeboard, so I'm kind of within the top 6 inches of my facility. I've set that up as my freeboard for my site. And this swale, that was an example I mentioned before. This swale is filling up, but since it's at a slope, let's say 2% slope, this whole volume could never really be used, could it? So when this facility overtops, we aren't actually filling up the whole volume. That's something that we couldn't visualize or easily understand without looking at a long section. And we'll see this long section, if I want to update something, move it, I can update these items directly within this interface. It may go without saying, but it's very nice to have helpful help. And I think we do. So when you are designing, one thing you probably don't have if you have Excel spreadsheets or some basic hydrologic tools, there's not a real good discussion of what in the world you're trying to do. And that's what we have in our help. So we have training material, we have very literal help, you know, this object means this exact thing, and a little bit more of a discussion about, great, this is what a stormwater control pond is and looks like. Okay? So really that makes using the software and really making the design just so much better, so much more transparent. You understand what you're doing and perhaps what design maybe you really do want. Okay, so I'm going to, let's look at XPDRAINAGE itself for a few minutes and kind of see these in practice. So we'll see here, this is our software, this is XPDRAINAGE. So as I mentioned here, we have this ribbon on the top, which really steps us through the design process of background information, design tools, you know, water quality volume calculators, that kind of thing, up through our results and analysis. This tree view on the left, if you're familiar with GIS or CAD, this is probably a pretty intuitive format. But we're going to manipulate a lot of data through this tree view. For example, later on I'll show that you can maybe import items directly through this tree view. Okay. So this, even somewhat simple model, is representing the visualization of a system. So we have drawn to scale, a catchment with facilities drawn. Now I might immediately want to look at a long section, and I can of course play through in time, right? I could play this facility filling up. They both are almost flooding. This hashed yellow area is the freeboard. So I know it's getting close. It didn't overtop. I would get a red indicator. But we can see how this facility, the timing of which the infiltration work. So you can see over a 2-day period, we fully infiltrate all of this flow. A couple of things here I didn't touch on. We have different rainfall events we can analyze. So perhaps here is just my water quality event. You'll see that I have just my one facility. Okay, my bioretention might treat just my water quality event. But then for a higher recurrence interval, a 5-year or a 100-year event, bypass flow would be attenuated in a swale. Okay. Now we also have something called phases. So you could represent your existing phase of your development. Okay, so here maybe it would be an existing phase. So my existing site I could compare to my developed scenario or my final design, which we were just looking at. reporting. It'll take a second for the view to update, but this is the just graphical reporting of how well these facilities and this entire treatment train performed. So, for example, I'm looking at a comparison of the 100-year event, and I want to make sure that I am reducing the total volume that discharges off my site and the rate at which it discharges as closely to that existing storm as possible. So you can see we can compare those items there. So I'm just going to move to kind of the unfinished product. So I was just looking at a completed project. Let's start with an existing site. So one thing I mentioned was I might want to automatically populate catchment information based on, let's say, CAD files, let's say GIS files. So I could right-click and then load areas from GIS. So here I have the catchment area. And you'll see I happen to have a template. So I know that I have the existing residential urban area has a certain type of characteristics. Well, I'm going to import this area based on that. Okay, so I have this existing area. Okay, so easy enough. So maybe I want to move to I want to compare the runoff from that site to my developed site. Okay. So my developed site, we'll see. Well, before I begin developing my site plan, which you can see there's already a layout there, maybe I will apply the deluge to my site. This will run for a second. And then now will show me how the flow is going to move across my site. So you can see where the flow moves, and right, the deeper it is, the bluer the water levels are. So from this plan, you can see that in between these buildings, this area here is where almost all of the volume naturally runs to, and then kind of through up and out the northern part of my site. So if I was looking at my treatment train, perhaps I will treat all of the water quality volume here. Okay, so my first flush volume I can treat all on site, and then discharge out to some swale or other facility just north of my site to have the higher events attenuated. Okay, so we can look at that right now. So I'll turn off my surface. So let's see, I could build my site quite easily. So let me select, these are the templates that I've created, so I can select the developed area. Perhaps I want to start with a bioretention system. This is the treatment train tool. So you'll see here I would just very easily click along, and maybe I would drain to a swale, as I mentioned. You see I can just select the next item. I can end the train. Okay, so now I've just created this treatment train. So I could start by perhaps, I want to make sure I snap to the file, and I can draw in the outline, okay, of my catchment area. This is mostly just to kind of prove that we can, right? So trace along. You'll see here that, of course, I have my 6.5 acres with all of my catchment information. So this is my developed template that I've already set up. So now I've drawn these facilities. The facilities have been set up vertically based on the surface in the model, though I didn't have the weirs at the end of my facilities automatically updated. So maybe I'll set these manually. So I'll add in kind of where those facilities should be in space, right, because I didn't have that automatically updated. So by updating those facilities, I could look at my profile. So see here, this is what I am representing. So all the flow drains to my bioretention and then overflows to my swale system. This is what we looked at a second ago in the completed model. Obviously, I could then run this system and get really the same results we were just looking at. When you run the model, you're going to right away get a table of, the quick volumes maybe you do want to check. So you can see the volume in, volume out, max inflow, max outflow. Okay, so yes, this table right here very quickly shows you really all you need to know at a glance. Further details, you could of course go back into a comparison of the phases. So I could look at the phases of existing compared to the developed scenarios. Okay, so I know we covered a lot of ground here. So I want to mention that there is a free trial of XPDRAINAGE available, and obviously it's available for purchase as well. You can just go to our website and you can download the free trial and get started. You can join our mailing list as well for news about XPDRAINAGE or other products. Further information, you can obviously contact amsales@xpsolutions.com. That was the email address that Nicole had mentioned previously. That's the end of my presentation, but thank you for joining. I'll be writing back to anyone who wrote in questions. Again, thank you very much for joining.